Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
When you say hypersurfaces, that they should be equidimensional of dimension 1 less than the ambient space. So, this is what I want to characterize, and they should, and hypersurfaces should mean that they are defined by one equation. So, this is what the theorem we will prove is the following. So, theorem so A is a finite type algebra over K. So, A is quotient of a polynomial algebra x1 to xn modulo the ideal A. Then the following are equivalent. One, A is equidimensional of dimension exactly 1 less than the ambient space, that is n minus 1, and 2 now what I before I write the statements to make them clearer, I am going to identify the spectrum of A, prime ideals of A to V of A. V of A simply means all those prime ideals in the polynomial ring which contain A, and then they will correspond to prime ideals in A and conversely. So, this is a closed subset in spec of K x1 to xn, and this is what do I mean by our ambient space, because with this identification we are thinking this is embedded in spec of K x1 to xn, in fact as a closed subset, right. In fact, not arbitrary embedding, the closed subset, and when I say embedding, that means it is a homeomorphism from this to this. So, this in its Zariski topology, and this Zariski topology coming from this actually a homeomorphism, close homeomorphism, close embedding, what one calls it. And the minimal prime ideals here will correspond to the minimal prime ideals here. So, they will be precisely the minimal prime ideals over this ideal A in the polynomial ring. So, the taken statement is every prime ideal which is minimal over A when you say minimal prime ideal, that means I am now thinking here, everything I am thinking in a spec of K x1 to xn. So, every prime ideal which is minimal over A is minimal among non-zero prime ideals in K x1 to xn. Okay. Third one, the radical of the ideal A is generated by a single element for some G in polynomial over K. So, that means you see here V of A will not change if I go to the radical ideal. And if you would have proved this, that will mean that this is defined by one equation. So, that is a hypersurface. Such a thing is called a hypersurface. So, that this equivalence will justify, this equivalence is in fact an analog of what we did it in linear algebra. Hypersurface in the vector space is defined by one equation. That is one less dimensional subspace in a finite dimensional vector space is actually it is defined by one equation. Okay, so let us prove this. So, proof, as I said, we will make the above, I will always make use of the identification that above I mentioned. So, so let me write M equal to, these are the all elements, all prime ideals in kx1 to xn such that P is minimal over A, this set. This is a finite set. In fact, these are precisely the minimal elements in the associated primes of the ideal A, kx1 x2 xn mod. This is same as min associated primes of kx1 to xn modulo A. And what do I want to prove? If I want to prove 1 implies 2, what do I want to prove? I want to prove that any element here is in fact minimal among all non-zero prime ideals in kx1 to xn. Okay. So, first of all note that if I take dimension of kx1 x2 xn, take any element here in M. So, if I take any p in M, then this dimension is a dimension of A by the image of P mod A, but this is n minus 1 because of our assumption, because we are saying A is equidimensional of dimension n minus 1. That means all minimal prime ideals will give, all grid spatial components will give the same dimension, and that is nothing but dimension of this. So, we know that for each M in M, dimension of kx1 x2 xn mod P is n minus 1. So, first of all, I know, because we know now the dimension of kx1 x2 xn, this dimension is n, and going mod P dimension drops exactly by 1. So, in particular P cannot be 0. If P were 0, this is not correct. So, P has to be non-zero first. Not only that, P has to be minimal among non-zero prime ideals, because if not, what will happen? If P is not minimal among non-zero prime ideals, that means P contains some non-zero prime ideal. Then 0 is a prime ideal in kx1 x2 xn, and another q will be there, and this P will contain that P will contain that q. If P is not minimal among non-zero prime ideals, then there will be q in between, and now this length I know it is n minus 1, because the dimension is n minus 1. So, therefore, this length, the chain will increase at least by 2. So, that will show that dimension of the polynomial ring will be at least n plus 1, but that is not correct. Therefore, that proves 2. So, that implies P is minimal element in spec of kx1 to xn minus 0. That is the meaning of the second statement, that the minimal element here. minimal among non-zero prime ideals of this. So, that is 2. So, that proves 2. So, 1 implies 2 we have proved. Now, let us prove 2 implies 3. So, 2 says every prime ideal P in the set M is minimal among non-zero prime ideals in the polynomial ring, and from here we want to conclude that the radical of the ideal A is the principal ideal. This is what we want to conclude. Okay, so take P, what is given is P is in M. Then we know that height of P has to be 1 because P is minimal among the non-zero prime ideals. So, there can't be any prime ideal in between 0 and this P. Therefore, height of P cannot be more than 1, and on the other hand it is less equal to 1. So, it is exactly 1. Now, where are we? This P is a prime ideal in the polynomial ring over a field kx1 to xn, and this polynomial ring is actually factorial. When I say factorial, that means unique factorization domain. Another usual word is used for unique factorization domains in a algebraic geometry, especially is a factorial. So, this means this every element, every non-zero, non-unit has a irreducible decomposition, and any two irreducible decompositions are essentially unique. That means the number of factors, and they are unique up to order and unique up to a units. So, I am going to use that fact. So, this simple lemma, but very useful all the time. So, in general, if you have a factorial domain, Aschim-Noetherian also, then every prime ideal of height 1 is principal. This is very simple. Let us finish off the proof. Proof is, so we have given a prime ideal of height 1. Let P be a prime ideal and height P is 1. So, therefore, P cannot be 0. 0 is a prime ideal. P cannot be 0. So, it definitely has one element, say small f in P. F is non-zero, but the small f is an element in A. So, therefore, it has a factorization. So, the small f, I can write it as pi 1 to pi r, where these are irreducible elements in A. Actually, they are prime elements, because you know in a factorial domain irreducibility and prime is same. So, they will generate a prime ideal. So, for example, if I look at pi 1, f is a non-unit definitely. So, it has at least one of the prime factor will be there. So, pi 1, for example, pi 1, this will generate a prime ideal, and it is definitely contained in P, and this is non-zero, and because P is height 1, there is no option but to have equality here. So, that will imply P is equal to generated by pi 1. So, what did we prove? We proved that every prime ideal in a factorial domain of height 1 is principal. Converse was we proved this Krull's principal ideal theorem. If you have a height 1 prime ideal, if you have a principal prime ideal, then height of that will be exactly 1. Okay, so now that is precisely the situation we have when P is in M, height P has to be 1 and therefore, P is principal. So, choose a generator for P. So, P is therefore generated by some element, let me call it, this generator will depend on this P. So, I will write GP for some prime element GP in the polynomial ring. Okay. And we are interested in now proving the radical ideal is generated by one element, right. So, which one element is, so look at the radical of A. Radical of A is the intersection of all the minimal primes. So, this is intersection P, P varies in M. M is precisely the minimal prime ideals over A. So, this is radical and P is generated by the GP. So, this is the intersection of ideal generated by GP. P is varying in M. This is a finite intersection and I claim that this is now generated by G, where G is the product, G is the product of GPs. This is a finite product. So, that is clear, because to prove that, you prove that G is here and each one of them is this. So, this, just check this, I would just write here check this, and you will have to use the fact that you are in a unique factorization domain. Okay, so that proves 3. Now 3 implies 1. So, we have given that radical of an ideal, the given ideal A is the principal ideal, and then from that we want to conclude that A is equidimensional of dimension n minus 1. Okay. So, suppose radical of A is generated by G for some G in kx1 x2 xn, and now what can you do? You have an element in a unique factorial domain, therefore, you can consider its irreducible factorization. So, let G equal to G1 to Gr be a prime factorization of G. Actually, we should say D, and up to order and up to a units. So, now Gi and Gj are different prime factors here. That means, the Gi cannot divide this and the other way. Okay, so G and Gi are primes, Gi are prime elements in kx1 to xn. So, therefore, they will generate a prime ideal. So, let Pi ideal generated by Gi, this is in spec of kx1 to xn, and it is clear also that if I take we know that ideal generated by G is the radical ideal of A, and which is intersection of Pi, I is from 1 to R. Because this equality is because, see, the G is the product. So, this ideal generated by G and this intersection is same. Therefore, in this case, M is in fact the set P1 to PR. And now I want to check that this A is equidimensional of dimension n minus 1. That means I should check that. So, I know the associate minimal elements in the associated primes, they are precisely P1 to Pr, each one of them is the principal ideal, and we want to check that the dimension drops exactly by 1. So, we need to check only that dimension of A modulo these Pi's. So, that is strictly speaking I should write Pi mod A is this ring is precisely dimension of this ring is k x1 x2 xn modulo Pi, but that is same as dimension of k x1 x2 xn modulo the ideal generated by the prime element Gi. And what do you want to check? We want to check this is n minus 1. But that is clear, because you see this is we have proved that if you go modulo an element which is a non-zero divisor, then the dimension will exactly drop by 1. So, therefore, because Gi's are prime elements non-zero, so non-zero divisor in a domain, therefore, dimension will exactly drop by 1 from this. So, this dimension is dimension of k x1 x2 xn minus 1, but this dimension we know that is n, so it is n minus 1. This is true for all I. So, therefore, A is equidimensional of dimension n minus 1. Actually, the dimension theorem I have used here to say that the dimension drops exactly by 1, but this also you can avoid by using dimension theorem. See, this is a milder use of dimension theorem. One can actually prove it by hand. The dimension is n minus 1. Similarly, also you know the proof k x1 x2 xn equal to dimension equal to n. Here also we have not, we do not really have to use the dimension theorem, it follows from normalization lemma. So, some of the things can be avoided, but anyway, since we have the machinery, we will use it. So, that proves this theorem.